Good morning and welcome to today's webinar, Air Sampling Headlines in Occupational Hygiene. This morning we have two presentations. First up will be Debbie Dietrich from SKC, followed by Adam Atkinson from SGS Leeder Consulting. Both presenters have vast experience in their fields and I'm sure you'll find them very interesting and informative. I'll now hand over to Debbie Dietrich, Vice President and CIH at SKC Inc.
Good day, Australia. I am so thrilled to do this transcontinental webinar featuring dueling accents with the single goal of providing the latest information to you, the occupational hygiene community. Thanks to SGS Australia and AirMet Scientific for working with SKC on this training event. Now, most of you hygienists work in several aspects of health and safety, but SKC and SGS work every day 100% focused on a niche of occupational hygiene, air sampling and analysis. So together we have selected 3 topics for this webinar that we feel are making news in 2015. First, respirable dust, including crystalline silica, manganese, and inorganic acids. So let's begin with issue number 1, respirable dust. You know, one of the first issues that I remember learning about as a student of occupational hygiene is pneumoconiosis, dusty lung. Sadly, pneumoconiosis is still a major cause of morbidity and mortality around the world. I was doing a little research to get some statistics on pneumoconiosis for this webinar, and I actually came across an article authored by Australia's own Dr. Timothy Driscoll from the University of Sydney School of Public Health. This article noted that there were about 386,000 deaths globally in the year 2000 alone due to past or current occupational exposure to particulate matter. Now, many of these deaths were related to, of course, crystalline silica. So our profession continues valiant efforts to try and control this hazard. Shown on this slide is the silica logo used in my country by US OSHA in their efforts to train workers. If it's silica, it's not just dust. So let's look at headlines in regards to respirable dust. First, absolutely lower occupational exposure limits for silica. Second, an ISO standard that defines performance criteria for respirable dust samplers. And last, new samplers to meet the criteria. Now, most of us working in hygiene for a while associate silica exposures with jobs in construction, abrasive blasting, foundry work, or mining. Recent headlines from US NIOSH, however, have focused on new high-risk jobs. First, fracking. NIOSH articles in the AIHA journal have noted that silica exposures at hydraulic fracturing sites are consistently over the OELS, sometimes 10 times the exposure limit. Another new area that NIOSH has been focusing on in their blog is the silica hazards from cutting, grinding, or polishing of what they call engineered stone countertops. This is what I call poor man's granite. Given the health effects from these exposures, scientific bodies, regulatory agencies have lowered exposure limits for crystalline silica in recent years. It was actually 2006 that ACGIH lowered the TLV for crystalline quartz and cristobalite to 25 micrograms per cubic meter. At year-end 2013, it was big news in the U.S. that U.S. OSHA finally published a proposed rulemaking lowering the exposure limit for all forms of respirable crystalline silica to 50 with an action level of 25. The proposed rulemaking definitely has not passed. You know, in our country, it actually has to have congressional approval from Washington, D.C., so we're not sure if that will ever happen, but we're hoping. Now, since the beginning of our profession, there have been some regional differences in the performance criteria used for respirable dust samplers. Now, when I first started in this profession 30 years ago, we were talking about the so-called BMRC curve that was used more like in Europe and possibly in Australia. In the U.S., we had different performance criteria for samplers. So in a move to consensus, most occupational hygiene organizations around the world, including ISO, the Committee for European Normalization, CEN, ACGIH, and Standards Australia, have now adopted ISO Standard 7708, something we should all know. ISO 7708 specifies a collection efficiency curve with a 50% or the same term, median cut point of 4 microns. For any of you that are new to hygiene or just crossing over from another profession, as a point of clarification, this so-called 50% or median cut point is the size of dust that the sampler collects with 50% efficiency. Now, in light of this ISO 7708 standard, aerosol scientists have done studies to determine flow rates using our old traditional cyclones that can match ISO 7708 with an acceptable level of vice. In Australia, a commonly used cyclone is the Higgins dual design, including the SKC plastic cyclone manufactured in the UK. At a flow rate of 2.2 liters per minute, this cyclone provides an acceptable match to the ISO 7708 criteria. Now, in the U.S., the SKC aluminum, or as you say, aluminium cyclone is frequently used, and it is listed as one of the sampler options in NIOSH respirable dust methods. The aluminum cyclone is operated at 2.5 liters a minute to match the ISO criteria. Now, in the late 1990s, a new cyclone design was brought to SKC by scientists from the University of West Virginia. West Virginia is a region rich in coal mines. The GS3 cyclone was designed to overcome orientation bias and electrostatic problems with the old Dorr-Oliver cyclone that is unfortunately still used by U.S. compliance officers only because it was written into the Federal Register. They're kind of stuck with it till this rulemaking passes. The GS3 cyclone was designed to match ISO 7708 at a flow rate of 2.75 liters per minute. This cyclone is mentioned by name in the OSHA proposed rulemaking on silica. Now, if you attended my course at the AIRH conference in Melbourne, you heard me make a plea for new respirable dust samplers. Most of the traditional cyclones are older than MICROMETER. They have been used for many years for previous criteria. Now that we have newer criteria, I believe it's time to consider new samplers. Adjusting the flow rate of older cyclones can provide a, quote, acceptable match to the ISO criteria, but why not use new samplers that provide a precise match to the new criteria? Our profession did exactly this for inhalable dust. We developed new samplers for new criteria. So I would like to introduce you to the latest development in size-selective dust samplers from SKC called parallel particle impactors, or PPIs. They are not cyclone samplers. They are impaction-based samplers like the IOM. Respirable PPI samplers provide a precise match to the ISO 7708 criteria. Now here's how they work. They have 4 holes or 4 inlets, and each of those individual inlets functions essentially as a separate impactor with a unique defined cut point. The air enters in through the inlets, large particles hit the impaction substrates and are scrubbed out, and smaller respirable particles are collected onto the filter for analysis. You use the exact same PVC filters for respirable dust, support pads as usual, and that you would use with cyclones. And the size of dust collected onto the filter will closely match the ISO 7708 criteria. Now, when we first came out with this design, we produced it only in a reusable anodized aluminum. But for convenience sake, hygienists came back to us and said, wow, we would really like to have a single-use plastic model, similar to like a DPM cassette, where we do size-selective sampling with a disposable plastic sampler. So we came up with this single-use model, and with this version, the impaction substrates are loaded and sonically welded into place by SKC. You have no loading, no assembly. It's more convenient, and being disposable, it eliminates the need for post-sample cleaning. With either the plastic or aluminum model, the filter should be pre- and post-weighed by the laboratory for gravimetric analyses. SKC does not provide PPI samplers with pre-weighed filters. Why? It is a standard of good practice for the filters to be pre- and post-weighed on the same analytical balance under the same conditions. SKC only offers PPIs preloaded with filters for chemical, not gravimetric analysis. Here you can see a plastic disposable PPI. It's essentially like a 2-piece cassette. There is an inlet and an outlet. But the inlet section has 4 internal pre-oiled impactor plates sonically welded in place that scrub out the larger non-respirable particles. And again, these impaction substrates are pre-oiled, so they have a 1-year shelf life. Otherwise, they'll begin to dry out. Like with filter cassettes, smaller particles are collected onto the filter in the outlet section for analysis. Now, SKC offers the disposable PPI models in a choice of flow rates, 2, 4, or 8 liters a minute. So this will facilitate use for short-term or TWA sampling. Now, most of us are used to using respirable dust samplers at flows near 2 liters a minute. So why the higher flow rate samplers? Well, NIOSH. NIOSH has been asking for this, and here's why. NIOSH reported in the Annals of Occupational Hygiene journal article that if you are sampling in a working environment near the TLV of 25, you may not be able to capture enough silica onto the filter for quantitative analysis at 2 liters a minute, particularly for shorter-term samples. So SKC developed not only a 2 liter per minute model, but also a 4 liter per minute model that can be partnered with a powerful personal pump that can handle the pressure drop, like the XR5000 as our most powerful pump. And we have an 8 liter per minute model to partner with a bigger pump, the Leland Legacy pump. I know this pump is bigger. NIOSH has been using it in their field studies. Again, you're using this pump for short-term samples. The guy's not wearing it 8 hours a day. So NIOSH says there hasn't really been that much pushback for this sampling with this pump. Now here you can see the performance of the PPI relative to the ISO 7708 criteria. It is a perfect match. No surprise. It is a new sampler specifically designed to match the criteria. That's why we pay our aerosol physicists. The performance data on the PPI samplers was published in the Journal of Physics, and electronic copies are available from me upon request. Okay, issue 2, manganese. This is one of my favorite topics. I just find it so interesting. If I talk to any of my hygiene friends in Texas, they all agree that manganese is one of the biggest concerns that they are facing. Some of the industrial hygiene labs in the U.S. tell me it is their #1 analyte. And here's why. Even low levels of manganese in welding fumes have been linked to a Parkinson-like illness called manganeism. Now, it is well known, people always kid Americans that we're always suing everybody. We are a litigious society. Well, and the American Society of Safety Engineers reports that there are thousands of lawsuits from welders due to the health effects from manganese and failure to warn. Legal experts predict welding fume litigation may rival that of asbestos. Well, think about it. There's a lot more people that are welders in the world than there are people that were exposed to asbestos. Now, the big headlines for air sampling are the TLVs for manganese. In the year 2013, ACGIH adopted both an inhalable TLV of 0.1 milligram per cubic meter and a respirable TLV of 0.02. And this respirable TLV is used to evaluate levels of manganese fume. As with other inhalable dust, the IOM sampler at 2 liters a minute would be used to collect inhalable manganese. I'm sure most of you are very familiar with this sampler since it is listed in Australian Standard AS360. But let's now take a closer look at respirable manganese samplers. As we just discussed, respirable dust samplers, that's a traditional thing, you can go with that. But many users have turned to the respirable PPI, particularly for sampling in welding. And the main reason are simply logistical advantages. The PPI is small. The plastic ones are very lightweight. They don't get in the way of the welder. With that visor on their face, it's just more comfortable. It is not a tipping hazard. If you accidentally invert a cyclone, all the big stuff ends up on the filter. That's not the case with the impaction-based sampler. No sampler cleanup is required if you're going with the disposable versions, and we also have a calibration adapter for the plastic models. You know, many professionals in the U.S., I know, like to do both gravimetric and chemical analysis of welding fumes. Again, if you want to do gravimetric, you need to coordinate with the lab to have them pre-weigh and the filter for you. Okay. All right, the last issue, inorganic acids. Now, some of you may be surprised to see inorganic acids as a headline in hygiene air sampling. Even SGS was shocked at AIOH conference when I told them that the #1 sorbent tube after charcoal is the special water wash silica gel for inorganic acids. Now on this slide, I listed the acids that I'm talking about, and I also give you a list of typical industries with exposures. Living in Texas, I mainly see acid sampling being done in petroleum refineries, where they use sulfuric acid and hydrofluoric acid in the alkylation process. Remember, the alkyl group's adding as CH3s to their product. In Australia, you may see a lot of acid sampling in mines. Acids are used in the leaching process to extract precious metal from the ore. You also see a lot of acids in electroplating and paper mills, to name a few. Given the high usage of the SKC Special Silica Gel tube for acids, it was huge news to us when NIOSH released new methods for these compounds late last year. Of particular note is that NIOSH changed from a sorbent sample tube to a filter sampler to collect these acids. NIOSH noted that filters are better able to collect acids because they are found both in an aerosol as well as a gas and vapor phase in industry. Also, filters could be used in size-selective samplers where appropriate. Keep in mind, the TLV for sulfuric acid is issued as a thoracic TLV. So the filter could be placed into the PPI that SKC has for the thoracic fraction. We have one both for respirable as well as thoracic. In the end, there are now 3 new NIOSH methods for acids. NIOSH 7906 is for hydrofluoric as well as particulate fluorides. It uses a dual filter system of a chemically coated and an uncoated filter in a single cassette separated by a spacer. NIOSH 7907 for hydrochloric, hydrobromic, and nitric acids again uses a dual filter system with one chemically coated and one uncoated filter. NIOSH 7908 uses an uncoated plain old quartz filter for phosphoric and sulfuric acid. NIOSH feels that these new methods are a significant improvement technically and reflect a harmonization with relevant ISO methods. One of the strategic goals of both NIOSH and OSHA is to work more closely with consensus organizations. I'm not sure if it's an issue of money, they can kind of all pool their resources or share their knowledge. Note, however, that NIOSH method 7903, the old method, using a water wash special silica gel tube, is still posted on the website. I checked it this week. It is still there. OSHA also has a method for acids using the special silica gel tube with SKC 226.03. As such, this tube is still available from SKC. Okay, I hope you found my presentation on sampling to be informative and useful. I hope it struck something that you have to address in your job. And I'll now look forward to Adam's portion of this webinar on analysis.
Thanks, Debbie, and thanks, Peter. The purpose of my presentation today is to give users of laboratory services some insight into how the results are generated and what they mean and what you can expect on the report. For this talk, I will be focusing mainly on welding fumes. As Debbie has mentioned, there's been a recent increase in awareness regarding the effects of welding fume exposure, particularly fumes containing manganese. As Debbie mentioned, prolonged exposure to manganese leads to a symptom known as manganism, in which the person displays effects similar to that of Parkinson's disease. This includes tremors, loss of balance, muscle rigidity, and slowness of movement. Even low-level exposure to manganese has been shown to affect workers. That includes mood changes, loss of memory. Between NIOSH and OSHA, there are several different methods that cover the analysis of welding fumes. Each of these methods involves collecting the metal onto a filter followed by analysis. The different methods each have a different digestion of the filter and a different analytical procedure. So basically, digestion is a process where heat and concentrated acids are applied to the sample. The purpose is to break down the sample matrix and get the metals into a solution which then can be analysed. So once the solution has been digested, typically an instrument such as an ICP AES is used for the analysis. This stands for inductive coupled plasma atomic emission. The digest is aspirated into the plasma, which further breaks down the metals into their elements. In the plasma, the metals are excited and they emit light, which can be measured in the emission spectrometry. Now, the benefit of this technique is the range of metals can be analysed in a single test. And the analyte suites are generally governed by the ability of the media to capture the metal, the effectiveness of the digestion. Alternative instruments can be used for the analysis, and increasingly ICP-MS is becoming much more popular for this analysis. ICP-MS stands for inductive coupled plasma mass spectrometry. MS has many benefits over using AES, and that is lower limits of reporting, and is also subject to less interference. It also has greater accuracy because you're measuring the mass as opposed to a light output. And as we can see from manganese, we're starting to concerns are looking at lower levels, so using a technique that is more sensitive has inherent benefits. This page lists a summary of all the methods available to choose from. As I mentioned earlier, the effectiveness of each of these methods is based on the ability of the media to collect the sample, the digestion that is used, and the instrument analysis. For metals analysis, there's many different digestion techniques available, each involving different acids or combinations of acids and different pieces of equipment to apply the heat to aid the digestion. Each of these different digestion techniques can and will produce slightly different results with different metals. For example, NIOSH 7300 uses a nitric acid perchloric digest on a hot plate. The chloric acid is used because it helps fully digest organic material. But under these conditions, it's been known to underestimate the concentration of manganese in the sample. So if manganese is a prime concern, then you should look at using an aqua regia type digest, which includes nitric acid and HCl. A good all-around digestion technique is to use the microwave, which employs high temperature and pressure and is very efficient. The microwave is listed in OSHA 7302. Being a fully enclosed digestion, it also enables lower level analysis and therefore reducing contamination. Microwave digestion followed by ICP-MS analysis is an excellent all-round technique for this analysis of welding fumes. If you have any further questions regarding all these different techniques, please discuss these with the laboratories before submitting the samples. For the next part of the presentation, I'll be discussing laboratory reports and what's on the reports and how to interpret them. Commonly, a question I get asked is, what is the PQL on a report and what does it stand for? PQL stands for Practical Quantitation Limit. And basically, it's the lowest reliable level the result can be quantified with an acceptable level of accuracy. Now, sometimes you'll see laboratories use LOR. Both LOR and PQL are roughly interchangeable. But both of these should not be confused with limit of detection, because limit of detection is the lowest amount of substance can be detected in the background. However, this result can't be reliably quantified, and the PQL is the lowest limit that can be reliably quantified with an acceptable level of uncertainty. Units are also something you make sure that you check on the report. You always make sure that you use the same units in your calculations in your report that is on the laboratory report. With any field measurement and laboratory measurement, it's vital that quality control is considered as part of the program. Quality control demonstrates the accuracy of the result and provides confidence in the result to third party and clients. Blanks are an important part of any QC sampling program and laboratory program as well. Blanks confirm that the contamination is not confirmed during the handling or the analysis. Blanks can also show that low-level detections are real and not background. Three common blanks to consider are trip blanks, which confirm that the matrix travelling to and from the site does not cause any contamination. Matrix blanks, which confirm the sampling media is free of contamination of the target analytes. And method blanks, to confirm the lab processes and handling is also not the cause of any contamination. Blanks are important because as analytical techniques improve, PQLs are reducing. Therefore, to provide confidence that results are real and not background, it is important to include blanks in any testing and sampling program. A common question I get asked is how to convert results from mass per filter or mass per tube into an airborne concentration. To do this, divide the mass of the filter by the volume sampled. Make sure, though, you consider all the units in your calculation. Save yourself time. You can ask the laboratory to provide this on the final report if you wish. Please ask this up front or on the COC and provide the sample volumes. If necessary, results can also be converted to ppm if applicable, and I've included the calculation in there because that's something, it's also a commonly asked question, or I've included a link to the NIOSH website which has the calculation there. Additional QC that should be considered is spike recoveries. The purpose of this is to allow an estimation of performance of the analytical procedure. Obtaining a spike recovery involves adding a known amount of the target compound to the sample matrix, typically the tube or the filter. Spike recovery samples are then analysed as part of the analytical batch. The amount recovered is compared to the amount spiked. Each analyte will have an acceptance criteria for the spike recovery, which must be met for the results to be considered valid. If the spike recovery data fails, then the cause of this should be investigated and corrected prior to reporting of the data. So why do spike recoveries? Well, it confirms that the analytical method and the batch of the samples have been analysed correctly. That is, quantified and identified the right target compounds. And also can be used to provide recovery corrected results, which are the requirements of some methods. To provide this service, we request that for each batch of samples, 3 extra tubes or filters are supplied. We'll then use these to provide spike recovery data and matrix blanks on the final report. Uncertainty is a process which laboratories use to estimate the errors in their results. As you can see from the phrases, competent laboratories know the quality of their results, their test methods, and are able to estimate the uncertainty of the results obtained from these methods. And ISO 17025, testing laboratories shall have and shall apply procedures for estimating the uncertainty of the measurements. The laboratories have been performing these calculations for quite a while, but we generally find that this information is not requested, but is there available if the client, if the user of the service needs it. So why do we measure uncertainty? Because every measurement we make has an error, and every step in the analysis has an uncertainty. Now, when you combine those all up, you get a total uncertainty. So for a laboratory process, for example, if you weigh an amount of sample, there'll be an error. If you make up a standard, there'll be an error. If you analyse it on an instrument, there'll also be an error. So the total errors can be combined to give a total uncertainty for that particular method. In practical terms, it gives a better knowledge and reliability of the result, and it assists in making better decisions based on the results. It also enables improvement in methodology, which I'll speak about a bit later. And the uncertainty statement gives a range in which the true value is considered to lie. So what does an uncertainty value look like? So for example, the uncertainty statement gives a range in which the true value is considered to lie. So in this example, 9.5 plus or minus 0.7. The true value is likely to lie close to the reported value, but may lie anywhere within the range. And that is because the uncertainty is based on a normal distribution, so still the most likely result is the result that is obtained. Just to complicate things further, it may possibly even lie outside the range. And that's because the way we calculate the uncertainty. So ISO's guide for calculating uncertainty is reported uncertainty shall generally be given with a 95% confidence interval. So therefore, in practical terms, that means there's a 95% chance that the results will be in the range that we specify. So for a 95% confidence interval, then we're 95% certain the results for the above mentioned will be between 8.8 and 10.2. But I must stress that the result is likely to, most likely to be at a given concentration. And that's because of the ISO's policy, it's a normal distribution. So as I mentioned earlier regarding uncertainty, it helps improve the reliability of results. And what we find with uncertainty is the result does vary with the results. So in general terms, what we find is if we're analysing low-level analysis and we get a result near the PQL of the method, we'll find that these results have the greatest uncertainty. An actual definition of PQL, or practical quantitation limit, is that the relative uncertainty is 100%. Therefore, if an analytical technique is close to the PQ, gives a result close to the PQL, which is also close to a guideline or a target value you're trying to meet, it'll be less reliable than using a technique where the PQL is much less than the guideline value. For example, using a more sensitive analytical technique does reduce the uncertainty of the result. And a practical example of this is using an ICP-MS as opposed to an ICP-AES will reduce the MU, particularly if we're looking at trace level amounts. Method uncertainty should also be considered when results fall just below a guideline value, as based on the uncertainty, the actual result could be above the guideline value. So in this instance, it should be considered. That concludes my presentation. Thank you.
Thanks, Adam. So thanks, Debbie and Adam, for your time today. Very informative and interesting presentations, and I hope to see you all again soon. Thanks very much.